Day 94 Notes, Advanced Algebra 2. Today we're working on some practice problems from the Holt worksheet. It's Holt 1-7 Practice B. We'll complete problems 1 through 8. Looking at number 1 first, we have the function g of x is equal to negative 4x plus 2. Now, we need to evaluate this function 3 different times. Once at negative 1, once at 0, and once at 3/2. That's what our instructions tell us at the beginning of the worksheet. So let me set up this first example here and I'll work through it. Then I suggest that you pause the video and practice the last two on your own. In the first case, we have g of negative 1, which means that any x value inside this g function needs to be replaced with the number negative 1. So let me show you how I would write this if I were doing this on a sheet of paper. I would rewrite the function with a set of parentheses in place of the letter x. This way I'll recognize that the number inside these parentheses will match the number that's inside these parentheses here. Now I have the ability to rewrite in a different color, so I'm making that stand out a little bit more, but I'm sure you'll be able to see the same when you're writing this on your page as well. We all know that the operation between two numbers, if there's no sign written, needs to be multiplication, and that's also confirmed when we look at the original equation again, negative 4 times x plus 2. Doing the math, we see negative 4 times negative 1 is positive 4 plus 2, simplified, is equal to 6. And we have this first function complete. I'd like for you to try the same in these next two examples for this function g. Pause the video and check your work. And here we go with the solutions. G of 0 is equal to 2 because negative 4 times 0 is 0. When we add that to 2, we get a total of 2. G of 3/2 is equal to negative 4 because negative 4 times 3/2, well, I thought of this as negative 4 times 3 divided by 2. Negative 4 times 3 is negative 12. Divide that by 2 is negative 6. Negative 6 plus 2 is negative 4. And here we have our two solutions for the function g. I would like for you to pause the video, work on 2, 3, and 4, each of these examples, and check your work. And here are the solutions to numbers 2 through 4, along with the work shown. Again, please consider showing your work in this fashion. Always begin with a set of parentheses that represent the original input value or independent variable. This way, it'll keep your math a little bit cleaner while you're trying to simplify the equation. The only thing that I found interesting in this set of problems was the problems associated with the function evaluated at 3/2. You have to be on top of your game here and remember how to work with fractions. In this case, in number 2, we have 3/2 that needs to be squared. Well, don't forget a number squared means it's a number times itself. So that's how I recognize that 3/2 times 3/2 would be 9/4. Then in the next line, to combine with subtraction, you have to remember to use common denominators. And to do that, the number 3 turned into a fraction over 4. And what did I have to do to change this denominator of 1 to a denominator of 4? Well, I had to multiply by 4. And if I do that to both the top and the bottom of the fraction, that leaves me with a new fraction that can be used in its place. So that's where the 12/4 comes from. And again, this is where the 9/4 comes from. As long as you keep your fraction rules in order, then you should recognize the solutions for these problems. Now let's move on and take a look at number 5 and number 6. Ultimately, the questions here should be answered in a similar fashion to what we saw in the practice problems above. We're looking for a solution to f of -2 and f of 0 given these two equations. The only difference here is that the instructions tell us to graph each function first, then evaluate. Now, I could come through and write this as x squared minus 4 and evaluate this at -2. That would then be -2 squared. Well, that's 4, and 4 minus 4 is 0. So I know f of -2 should be equal to 0. Now, I don't want you to solve this using algebra this time. I want you to use a graphing method. Our instructions tell you to graph first. So in order to do that, we need to set up a graphs page on our graphing calculator. So I'm going to switch to the graphing calculator now, and this is what it should look like when you open it up on your computer. We're going to add a graphs page, and now we'll enter our equation. This equation is x squared minus 4. It's a simple equation, and we'll press enter here. It's here that you should recognize that in order to evaluate a function at a particular point, we must investigate the function's value when given a particular x value. And a value from our domain will result in a value on this range. Now, for the first part of the question, we're asked about what happens to this function when evaluated at a -2. So that means marching from this center point, our origin, we need to go left 2 units and then up or down until we reconnect with the graph. Well, in this case, we don't have to go up or down. We're right here at the origin, and that explains why f evaluated at -2 is equal to 0. But let me show you another way that we can evaluate this using the graph without necessarily looking at the graph or counting its position on the axis. If we switch over to our graph and use the menu button, we can trace the function at a particular value. So I'm choosing menu, option 5, and then option 1. We're going to graph trace. And you'll notice that this little cursor shows up on your graph. Now, we lucked out here. It started at 0, so there's our result already. F evaluated at 0 has to be -4. And so just by inputting our equation into the graph, we were able to find these two solutions pretty quickly. But let me show you again this one more time if we were dealing with f evaluated at -2. See, we lucked out here. We started at x equals 0, and that's the first result that popped up. But if I wanted to evaluate this at -2, since I've already called the graph trace command, all that I have to do is type the number -2. There was no entry box on the screen. I just started typing, and that's all that you have to do. Once you start typing, you can press enter, and the calculator will return your result. It'll automatically move this cursor to its position, and you can see the result of the function displayed in the bottom right. Let's try that again with the next example. So I'll press the tab key to bring up my formula bar, and I'll delete this equation. And now I need to write 3 halves. So I'm going to press Control and then the fraction bar to get this fraction in place. So we'll type the number 3. 3 in the numerator. Press the down arrow to put 2 in the denominator. I'll move to the right and call my independent variable x and add 1. Now I also have to have a negative sign, so let me move to the beginning again and type -3 halves x plus 1. And here's our graph. Now to calculate those two numbers, let's go to the menu key, then trace, and select graph trace. Well, again, we got lucky. Our cursor was left at -2, so I see that result. F evaluated at -2 is equal to 4. And then I switch back to the calculator. Now, f evaluated at 0. Again, the graphs trace command is on. We can see that in the upper left-hand corner. I'll type the number 0 Again, there was no cursor for me to select, no text box for me to choose. I'll just press the number 0, and it'll automatically pop up on screen. And I'll press enter, and it shows me the result here, 0, 1. So f evaluated at 0, or f of 0, is equal to 1. Again, this command is a really helpful one when calculating results from functions, and it moves very quickly. A lot of times it's easier to use this rather than trying to count these little hash marks on the graph individually. Let's move forward to our last questions on this assignment for today. Number 7 is an interesting question. In it, we work on converting values of currency. Now, the first thing that we recognize is that $1 US is equivalent to $1.24 Canadian. So we might think of that portion of the function this way. I'm going to write C of x for the Canadian exchange is equal to 1.24 times x. Now look closely. What this means is for every input x, I multiply by 1.24. Or in other words, for each dollar that I input into this function, I multiply it by 1.24, and that turns the US dollar into Canadian dollars. I could do the same for the euro in terms of x, or dollars. In euros, 1 US dollar is equivalent to 77/100ths, or 0.77 euros. Unfortunately, starting with these two formulas will lead us in the wrong direction, because these two formulas transform US dollars to either Canadian or US dollars into euros. And that's not really what our objective is here. Our objective is to start with Canadian dollars and transform them into euros. So let's think of it this way. The given information shares with us that 1 US dollar is worth 1.24 Canadian dollars, and 1 US dollar is worth 0.77 euros. So at least we have these two values that are connected through the US dollar. In essence, what this is telling us is that we have $1.24 Canadian and 0.77 euros, and they're equivalent to one another. Well, to change from Canadian dollars to euros, let's subtract these two numbers, and we see the difference between these two values is 0.47 units. So if I had my number in Canadian dollars and I subtract 0.47 from that, that will change my Canadian dollars to 0.77 euros. And this happens for each Canadian dollar. Therefore, if we write one more function, this time we'll call it f of x because this represents the function that we're looking for. If we start with x amount of Canadian dollars, again, not US dollars to something else, but we're starting with Canadian dollars, and subtract 0.47 from each of those Canadian dollars, we should have a value for our euros. If I evaluate this function at 5, f of 5 would equal x minus 0.47x. We're evaluating this equation at 5. So we have 5 minus 2.35. I did this calculation off screen. And then 5 minus 2.35 is 2.65. So again, f of 5 is 2.65. Well, what does this mean? According to the formula that we just created here, this means that $5 Canadian on this day is worth 2.65 euros. Now, I'll admit that this was a more complicated problem than I would have originally intended, but it's a nice way to see how looking at a particular function might put you in the wrong direction if you're not careful recognizing what your input and output values are. Let's take a look at a more straightforward example in number 8. PC Haven is selling computers right now, and their sale says that you can save 15% and $200 when you purchase a computer from them. Let me share something with you about sales. When they say that you're saving 15%, another way of looking at that is saying that you're paying only 85% of the original price. Now, where did the 85 come from? Well, 85 and 15 will equal 100, or 100% of the original price. So this is a good trick that we use when we're talking about discounts. Rather than focusing exclusively on how much the discount is, instead we should focus on the percentage of the original that we're going to pay. So let's think of it this way. When we're writing a function, f of x says we're going to write a function that changes the letter x. Now, we'll let x represent the original price. If we were saving 15%, then we need to only pay 85% of the original price, so 0.85 times x. Now, in addition to paying only 85% of the original price, we're getting a $200 discount. And if we're getting a discount, that means we're subtracting $200 from that price even further. And as an example, if I am inputting a value f of 2,500, that would be 0.85 times x minus 200. Again, that x was 2,500. Off the screen, I calculated that 0.85 times 2,500 is 1,700. We still need to subtract 200 from that. This leaves me with 1,500 as the result. So f of 2,500 is 1,500. What this means is a computer originally priced at $2,500 is on sale for $1,500. Now, it's interesting to note that there was a difference of $1,000. So as a side note here, we're going to indicate that we saved $1,000. But that's not always going to be the case. If you tried a different number in place here, let's say that you were buying a more expensive model, f of $3,000. So let's say you bought a computer that was going to be $3,000. You'll find that the final price is actually only $2,350. So what was originally $3,000 is now only going to cost $2,350. Now, I did just recognize something here. I made a mistake with my calculation. When I was working with the calculator, I only entered $2,000 as my price. So let me correct that here. Actually calculated this function at 2,000 originally. Now, if you were doing your work on your own and you found that the original price was 2,500, let me show you what that would have been, what the sale would have been there. And actually, we didn't save $1,000. We only saved $500. Let's get this squared away. So we saved $500 had we bought a computer that was $2,000, but the function evaluated at $2,500 as we originally intended is 1925. So when we look at these three examples, we actually saved $500 when we bought a computer that was $2,000. We saved $575 when we bought a computer that was originally $2,500, and we saved $650 when we purchased a computer that was $3,000 originally.